Good afternoon, all. My name is Ravi, working as Assistant Professor from Marri Laxman Reddy Institute of Technology and Management. My subject name is Flat, Formal Language and Automata Theory. Today, topic is Introduction to Flat. We will see about Automata Theory. A study of abstract machine or abstract device is called automata theory. Like abstract machine or abstract device. If we give input string to abstract machine, it will process by changing the states from one state to another state. Then it will the string is either accept or reject. Finally, it will recognize the language. If we give input string to the abstract machine, while processing this abstract machine will do changing the state from one state to another state. Finally, the string is accept, otherwise it will reject. The string is reaching final state, it will accept, otherwise the string is rejected. Next is types of automata. We are having four types of automata. Four types of automata. The first one is finite automata. Second one is push down automata. Third one is linear bounded automata. And finally, fourth one is Turing machine. These four are abstract missions. One is finite automata, second one is push down automata, third one is linear bounded automata, and fourth one is Turing machine. The language, so coming to finite automata, it contains finite number of states. Then it's said to be finite automata. The language which is recognized by finite automata is regular language. Regular language is recognized by regular language is finite automata. The finite automata is recognized one language. That language is called regular language. Next, push down automata. Push down automata is nothing but finite automata plus one stack memory. One stack memory. The language which is recognized by push down automata is context free language. The context free language is generated by context free grammar. The third one is linear bounded automata. Linear bounded automata is nothing but finite automata plus two stack memory. The language which is recognized by linear bounded automata is context sensitive language. Context sensitive language is recognized by context sensitive grammar. The final one is Turing machine. Turing machine is nothing but finite automata plus unlimited memory. Unlimited memory. Whereas finite automata, there is no memory. Yeah, Turing machine is having unlimited memory. The language which recognized by Turing machine is recursively enumerable language. The recursively enumerable language is generated by unrestricted grammar. So conclude this: finite automata, there are 4 types of automata. One is finite automata, second one is push down automata, third one is linear bounded automata, and fourth one is Turing mission. In finite automata, the language is recognized by finite automata is regular language. The regular language is generated by regular grammar. The language is recognized by push down automata is context free language. Context free language is generated by context free grammar. The language is recognized by context sensitive language is the context sensitive language is generated by context sensitive grammar. The language recognized by Turing mission is recursively enumerable language. The recursively enumerable language is generated by unrestricted grammar. These 4 are abstract missions. So now we will discuss terminologies. So first one is symbols, second one alphabet, third one strings, fourth one language, fifth one clean closure, or else sigma star, sixth one positive clean closure can represent sigma plus. So first one, symbols. Symbols are entity or object. For example, A, B, C like Z. These are English alphabet. And 1, 2, 3, so on. These are numeric alphabet. ABC and 1, 2, 3 like special symbols, hash and at the rate. These are symbols. Next, alphabet. Alphabets are set of symbols or collection of symbols. Alphabet we can denote it sigma. Sigma means A, B, C to Z and 0 to 1. These are the English alphabet and numeric alphabet. Next, string. String is collection of alphabets. It is denoted W. Mod W is, we can represent length of string. Length of string. Next, language. Language is say set of strings or collection of strings. For example, L is equal to A, AB, AAA, ABAA. These are strings. The string is the language is denoted by L. Clean closure. Set of all strings chosen over from sigma star including epsilon. This clean closure including epsilon. Coming to positive clean closure, excluding epsilon. Excluding epsilon. Sigma star is nothing but including epsilon. If language having 0 or more times of A. First 0A, 1A, 2A's, 3A's, so on. Any number of A's. Coming to sigma plus, excluding epsilon. If we take language, one or more times of A. So here, including epsilon, we can call it as clean closure. Excluding epsilon, positive clean closure. These 5 things We are discussing entire flat. First one is symbols. Symbols are entity or object. Coming to alphabet, collection of symbols. Strings, collection of alphabets. Language, collection of strings. And positive clean closure, including epsilon. Sigma star is nothing but including epsilon. Sigma plus excluding epsilon. Language is nothing but set of all strings or collection of strings. It is denoted by L. Example, sigma is equal to a comma b. The language is a p. One length, two lengths, length of the string 3. Here this is 1, this is 2, this is 3. Length of the string is 3. Clean closure, the set of all strings chosen over an alphabet. Sigma length include epsilon. Positive clean closure, the set of all strings chosen over an alphabet excluding length, excluding epsilon. Next, coming to finite automation model. This is the input type. Input type is divided into cells. Each cell we can put one alphabet like either 0 or 1 and A, B, like that. Read write head, it will read only one item from that tape. At a time, only one item from left to right. Finite state control is changing the states internally from one state to other state, next state. For example, Q0 is one state. Q0 on 0, it will move to Q1. This will do by finite state control. This is the after receiving final state, the string is accept, otherwise reject. It will not reach to final state, it is reject. If it reach final state, it will accept. So a finite automation is a mathematical model of computation used to recognize patterns or language. Formally, a finite automation is defined as 5 tuples: Q, sigma, delta, Q0, finally F. Q0 represents non-empty set of states, number of states. Sigma represents input alphabet. Delta represents transition function. Q0 represents initial state or start state. F represents final state or accept state. So finally, finite automata contains 5 tuples. First one is finite number of states. Q represents, and sigma represents input alphabets, either 0 or 1 or A comma B. States are nothing but Q0, Q1, Q2, like that. Next, delta is transition function. This edge represents transition function. This circle represents vertices, means states. This edge represents transition from state Q0. For input symbol 0, it will move to next state, which is Q1. Next, Q0 is initial state and F is final state. So here start state we can represent arrow and Q0. This circle and arrow represents start state. This double circle represents final state. This arrow, this Arrow represents transition function. This 0 and 1 is input symbols. This is called transition diagram. Next, structural representation of automata. The first one is state diagram or transition diagram, then transition table. First we need to construct transition diagram, after that transition table. Here states nothing but Q0, Q1. We can represent circles. Here Q0 is initial state, arrow pointing to the state. Final state, double circle. And transitions, directed edges labeled with input symbols. Transition table. Row contains state. States. Here two states are there, Q0 and Q1. And column represents input symbols. Here input symbols are 0 and 1. So this is nothing but states are input symbols. Row contains states, column contains input symbols. We need to find out for state Q0, for input symbol 0, where it go, Q0 on 0, Q1. From state Q0 on input symbol 1, it will go to same state. From Q1 for input symbol 0, it will go to same state again. From Q1 on input symbol 1, it will move to initial state Q0. This is the transition table. Next, there are two types of finite automata. First one is deterministic DFA, deterministic finite automata. Second one is non-deterministic finite automata. Previous we can see state diagram, circles and arrow pointing to the initial state, and double circle represents final states, and this edge represents the transition table having rows and columns. Row contains states, column contains input symbols. Now we will see finite automata contains two types. First one is deterministic finite automata and second one is non-deterministic finite automata. In deterministic finite automata, if you want to read input symbol from state Q0, input symbol 0, it will move to only one path, only one way to the next state, only one path. For state Q0, input symbol 0, it will move to only one state, which is Q1. Only one path or only one state. DFA contains only one path. There is no choice. NFA, non-deterministic finite automata, NFA contains many paths. Like for state Q0, for input symbol 0, either it will go to Q1, and next, for example, QF state. If you want to take QF 0 from state Q0 for input symbol 0, it will go to either Q1 or QF. So here choice is there, whereas DFA, in DFA there is no choice, only one way. In NFA there is many ways for input symbol. So here choice is there. In DFA there is no choice. So now stop here. The next class will continue to examples of DFA and NFA and conversion of DFA to NFA. Thank you.